Hello everyone, my name is Ryan Scott, and today I'm going to present a tool that I've developed at Galwa with the help of collaborators at NASA. The name of this tool is Copilot-Verifier. There are two parts to the name Copilot-Verifier. The first part is Copilot. Copilot is a framework for performing runtime verification, which is to say, Copilot allows you to monitor programs during their execution and detect if the program violates certain properties and then respond to them. One of Copilot's key use cases is for cyber-physical systems such as aircraft. Copilot takes a program written in a special-purpose domain-specific language, and then it translates it into a runtime monitor that's written in C. Copilot itself is not new. It was originally developed several years ago, and it's been undergoing continued development at NASA since then. The new part is the verifier part of the name. That refers to the fact that this tool formally verifies that the monitor code is correct. Now, I won't delve deeply into the technology of formal verification in this talk, but roughly speaking, formal verification means that every time Copilot-Verifier runs, it also does a mathematical proof. The proof tells us with near perfect confidence that Copilot didn't make any mistakes when constructing the runtime monitor. That's important for two reasons. One reason is that the C program is typically way too complex to audit by hand. And the other reason is that if there's an error in the monitor, that could be catastrophic. It could cause your unmanned aircraft to malfunction, for instance. So in this video, I'm going to demonstrate the Copilot-Verifier tool and use it to show you how you can make the case that your Copilot programs can be trusted to work correctly. The eventual goal here being that we can use the verifier to argue that Copilot programs are trustworthy enough to be used in safety-critical domains such as aircraft. So before I get too deep into the details of the tool itself, I want to take a step back and describe the problem this tool is trying to solve. I'm going to give you a very brief overview of Copilot, and I'm also going to show you how you can compile a high-level Copilot specification down to a low-level monitor program. And the broad theme here is that the monitor code is machine generated and quite a bit more difficult to understand than the original Copilot spec. So the challenge is trying to gain confidence that the generated monitor code has the same behavior as in the original spec. So note that Copilot, which I have a very simple example of a Copilot spec on the screen at the moment, Copilot is a domain-specific language that's embedded in the Haskell programming language. And when you use this language, it's usually because you want to write a specification for some system. The basic units of computation in a Copilot specification are streams, like this one. Conceptually, streams are infinite sequences of values, and values can be anything from integers to floating point numbers to booleans and even more complex, larger types like structures and arrays. Each element in a stream represents one moment in time, and in this sense, you can advance time forward by going through all of the subsequent elements in a stream. So streams are really important. And they're important enough that sometimes I'm going to just call Copilot specifications stream programs. So if you hear me talk about stream programs in the future, that's what I mean. All right, let's start off with this very simple example that I have on the screen. In this specification, our goal is to check properties about the Fibonacci numbers. We're going to encode the Fibonacci numbers using this fib stream here. That is to say, we're going to encode it as a stream of 32-bit integers. This code might look a bit familiar if you have some experience with functional programming languages. The idea here is that the first and second elements of the stream are 1 and 1, the first and second Fibonacci numbers, and then all of the subsequent elements of the stream are computed recursively by adding together previous elements. So now that you have this fib stream, as long as you keep advancing time, you can compute larger and larger and larger Fibonacci numbers. Okay, so that's the basic idea. And before we go on, I want to mention that one thing I'm not going to do is try to give a comprehensive tutorial on Copilot itself. There's two reasons for this. One is that there's a lot of material about Copilot you could cover, and I only want to focus on the parts that are new with Copilot-Verifier. The other reason is that actually NASA has already recorded a video tutorial on Copilot. So if you want to learn more about Copilot, I'll leave a link to that video tutorial so that you can watch it. All right, so let's take a look at the interesting part of this program, which is this, the actual specification part. The important parts of the spec are these two trigger functions, even and odd. And as their name suggests, these are going to check if the Fibonacci stream has even or odd numbers. The idea behind a trigger is that you have some property that you check for, and the property is represented as a Boolean stream. So here we have a Boolean stream of whether a number in the fib stream is even. So it'll be true if it's even, false if it's odd. And then for this trigger, we have a Boolean stream where if the fib stream has an odd number, it'll be a true, and if it has a even number, it'll be false. All right, and anytime you get a true value in this Boolean stream, the trigger will fire. So this is a really simple example. It's just checking if Fibonacci numbers are even or odd. But in a larger example, you might imagine that you will be checking really important properties with trigger, such as whether the temperature is too high or something like that. Typically, if a trigger fires, it means that something interesting has happened in your program and you should take action to respond to it. Okay, so once you have a specification, the next thing to do is to actually run it. And there's a couple ways to do this. One is to use Copilot's built-in interpreter, which lets you execute the specification within Haskell. So I have a window at the bottom which lets me do this. So let's go ahead and run this specification using the interpreter. Okay, here we can see what the interpreter's output is like. This will print a table where the x-axis contains the triggers, the x-axis will contain the triggers in the specification, and then the y-axis, which is here, this will contain a bunch of cells saying whether each of the triggers fired at a given moment in time or not. As you can see, the output is basically what we would expect. On the first time step, we have the number 1 in fibs, and that's an odd number, so the odd trigger fires and the even trigger doesn't. Similarly for the second element in the stream. With the third one, we get 2, that's 1 plus 1. This time, even fires, but not odd, and so on and so forth. And if you look at that, those are the first 6 Fibonacci numbers, so we now have a pretty reasonable amount of confidence that we've specified the behavior of the Fibonacci numbers correctly. Okay, so that's one way to run a Copilot program. Another way you can run it is to compile it to C and actually turn into an executable that you could use in a cyber-physical system of some kind. So let's go ahead and show how that works. And the way I'll do that is by using this compile function, which I'll uncomment here. This thing will take the specification and convert it into an executable one, and then auto-generate some C files with the name demo1 in front. So let's go ahead and do that. Reload the program. Okay, so this time, in addition to printing out the interpreter, it actually generated some files on the side. So let's see what that looks like. All right, so here is the C version of the specification on the left. I'll warn you, this is machine-generated C code, and it can be pretty intense to look at. So let me get rid of that window. Yeah, I would not worry about trying to understand this line by line because there's a lot of stuff going on here and it could be kind of subtle. I'm just going to point out some of the highlights here. So the first thing that I would point out here is that there's an array here. And this is a pretty important thing because this is what implements the fib stream on the C side. So the idea here is that we're trying to sort of, emulate the behavior of an infinite stream, but we're in C, so we're actually only going to use a finite amount of memory to compute an infinite stream. And the way that we do that is by using some clever array trickery to only store a cross-section of the stream at a given moment in time. So when we first start out with the program, it's going to contain the part of the stream that has the numbers 1 and 1. And then as time goes on, we will update elements in this array to have more and more elements from subsequent Fibonacci numbers. So eventually we'll put in 2, 3, 5, 8, and so on. So I'm not going to go into that aspect of Copilot in a lot of detail, but note that this kind of array bookkeeping code can be pretty subtle. So that's one thing that we really want to check for in our verifier to make sure we didn't screw that up. And then another thing I want to point out at the bottom of this file is this step function. This is one of the more important things in the file because this is what kind of implements the passage of time in C. So again, don't worry about understanding this code line for line, but if you squint at it, you'll notice some kind of broad themes. One is we have these guard functions here, and these are basically what implement the triggers on the C side. So each of those guard functions will check whether the even and odd triggers conditions are met, that is to say, whether we have an even or odd number in the stream. And if that's the case, then we will fire the corresponding trigger functions, which, as you can probably imagine, are also named even and odd. And then after we've done that, we will compute the next Fibonacci number and then insert it into the array, making sure that we put it in the right place and do all the necessary bookkeeping. Again, this stuff is pretty subtle, and don't worry about trying to understand it just from a glance. Okay, so the last thing I want to point out is that we have these even and odd functions here, but somewhat surprisingly, we don't actually have an implementation for them on the C side. The only thing that we have, if I open this file, we have these forward declarations, but we don't actually have any code that implements them, and that's on purpose. The reason for this is because a Copilot monitor is not a standalone program in its own rights. It's intended to be linked against a larger application of some kind. And then it's the responsibility of that application to implement all of the trigger functions. So depending on what your application does, you might want to respond to an even number or an odd number differently. So to give you an idea of what that is like, I've written a really simple example of an application you could link this with. So let me open that up. And let me close that to give more space. Okay, so here's a really simple demonstration of what an application might look like. So we've implemented both even and odd, and they don't really do much in this example. They just say we've encountered an even or an odd number, and it will also print out the value of the number. And then the main function will just iterate through 6 iterations of the stream, and then it will execute the corresponding triggers on each of those steps. So to give you a sense that, this isn't all just smoke and mirrors, you can actually run this stuff. I'm going to compile this application and show you what that's like. So let me go ahead and do that. Demo 1 driver, and we need to link that against that. Okay, and then if we run this, we can see that it actually does stuff. And moreover, it prints out the same numbers that we saw in the Copilot interpreter, and it correctly identifies whether they're odd or they're even. So that's pretty cool. This gives us a reasonable amount of confidence that the C implementation of this Copilot spec works correctly. But one thing I want to highlight here is that this is only just the first 6 numbers. So how do we know that the behavior of these programs will continue to be the same for all possible time steps? We can't just do that by running the programs. I mean, there's an infinite number of time steps you could consider, so that is not going to work. So another way we could try to convince ourselves that they're correct is by opening up the C file again and staring at this really intently and trying to convince ourselves that these 2 programs here are the same. But that's tricky, and there's a lot of details going on in the C code, and it's pretty easy for a human to overlook an important detail that could possibly introduce a bug. So because of this subtlety, we need something a bit more rigorous. And that's where our Copilot-Verifier tool comes into the picture. What our tool does is that you give it a Copilot specification, such as the one on the left as an input, and then it will prove that the semantics of the generated monitor correspond to the semantics of the original spec. And the way that you do this is with a call to this verify function. So this will basically do all the same steps as above, except at the very end, it will invoke the verifier on the semantics of the 2 programs and check to see if they're equivalent. So let me go ahead and demonstrate what that's like. Oops, I need to save and reload that. Okay. So this time, if I run it, we can see there's a bit more output from the verifier. What it's doing now is that it's basically encoding each of these two programs that I have above into a format that SMT solvers can understand. And then it constructs a series of proof goals to check to see if the two programs match each other. So that's what you see here with these proved 2 out of 2 and proved 18 out of 18 goals. It sort of does this in 2 steps, which is why you see the goals split up like that. The high-level idea here is that if the SMT solver can successfully solve for each goal, then we have a mathematical proof that the two programs are the same. Basically, that means that all the streams on the Copilot spec have equivalent values in the corresponding arrays on the C side. All of the triggers in the original spec fire in the same ways on the C side, and so on and so forth. That's a bit of a hand-wavy explanation, but I'm going to go into how that aspect of things works in a little more detail later. But the takeaway for now is that if you get this kind of output from the verifier, which says you've proved all the goals, then we've successfully shown through formal verification that the two programs behave in the exact same way. And also, we've managed to automate basically the entire process. The only thing that you have to do as a user is call this verify function, and then our tool will do the rest, which is pretty neat. All right, so the example I've shown here is kind of simple. It's useful for teaching purposes, but it's not really more complicated than a Hello World program. So I want to show some examples of more interesting things that are slightly closer to things you might actually use in the real world. So one example that I've prepared is a thermostat program. And the idea behind this program is that it's going to check to see if your thermostat is within an acceptable range of temperatures. In this case, the range is -50 to 100 degrees Celsius. And then the idea is that if the temperature exceeds that range, if it goes too high or too low, then a trigger will fire saying that, hey, your temperature is too high or too low, and then the application will probably respond by trying to lower the temperature and bringing it back to within the acceptable range. And the reason that this program is more interesting than the previous one, in my opinion, is because it does stuff with floating point math. If you look at this stream here, which computes the temperature in Celsius, it does stuff with floating point division, multiplication, so on and so forth. And I'm not going to go into it in too much detail here, but it's worth noting that trying to encode all the semantics of floating point numbers in an SMT solver can sometimes be a bit interesting. So the verifier has a bit more work to do on this program. So I can actually show you what that's like. If I run the verifier on this program, then you can see that it has to do more work this time, partially due to the floating point math involved and partially just due to the structure of the program. There's a lot more goals that we have to give to the SMT solver. But luckily, if you wait long enough, this should succeed, fingers crossed. And beautiful. Okay, so we can see that the verification succeeds even with the extra amount of stuff that it has to do. So having shown that, the last example that I want to show is this one. And what this is an implementation of what is called the Wellclear violation algorithm. And what this Wellclear violation algorithm does is it helps unmanned aircraft avoid collisions with other airborne traffic. And I'm not going to really go into the detail of what this algorithm does, other than to say that it uses a lot of sophisticated floating point math to get the job done. So if we scroll down a bit, we can see that at various points we have to multiply vectors, we have to compute the square roots of things, calculate lengths and norms of vectors, and a whole bunch of other stuff like that. So there's a lot going on in this example. It's one of the more complicated things we've given to the verifier, but luckily the verifier is up to the task. It is able to prove everything about that, and that's really exciting. So we have some confidence that we can actually use the verifier on large, useful examples like this one. Okay, so now that I've said all that, you might be wondering at this point, well, what exactly does it mean for an SMT solver to verify that these programs are correct? What is actually going on? If you want to know, I'm going to sort of give you the slightly less than high level look into what's going on so that you can have some confidence that it's actually doing the right thing here. So in particular, let me go back to this first example because I think this is probably the easiest to explain. So when you run the verifier on this example, I have instructed the verifier to print out all of the proof goals that get sent to an SMT solver so we can actually open them up on the side. And let me make that slightly larger. Okay, now this is the sort of raw format that an SMT solver looks at, and this is where most of the interesting work happens. If you don't know what SMT solvers are or how they work, don't worry. I'm not going to expect you to know everything that's going on here, but I just want to sort of point out that most of these proof goals are sort of derived from different parts of the specification or the generated C code. And if you squint, you can notice some broad similarities. For instance, the definition of the fib stream, we have to do addition, and as a result, there are various parts of the proof goals that talk about BV add. That's short for bit vector addition, and it's called bit vector because we encode integers in an SMT solver using the bit vector theory. And then similarly, we have to do things involving modular division on the specification side. So you'll see some calls to this BVUREM function, and that's short for bit vector unsigned remainder. Which is basically what implements that on the SMT solver side. So it's not exactly a one-to-one correspondence. The verifier has done a lot of optimization on these queries to try and make it so you can solve for them faster. So you can't really, go through this line by line and easily identify where it comes from the original spec necessarily. But do note that this is basically encoding of all the different things and obligations that we have to solve for in order to know that the semantics of the two programs coincide. So there's a lot more I could say about what's going on here, but that's sort of beyond the scope of this demo. So if you want to read more about how this all works, I'll include a link to a paper that we recently wrote about this idea, which explains this more. Okay, so I think that's more or less the last time we need to look at that. So before I move on, I want to give you some confidence that the verifier is doing the right thing. It's easy enough to see a message like this one where it says prove 18 of 18 goals, but how do we know that it's actually checking for all the things it needs to check for? I think the best way to demonstrate this is to show what would happen if there were a bug in Copilot that caused it to generate incorrect C code. So what we're going to do is open a part of Copilot C backend and then see what happens if we introduce a bug. So let's go ahead and do that. So I'm going to go over to the side and go to this file. Okay, so what I have in front of me here is sort of the part of Copilot that translates each of the stream operations into the corresponding C code. So we have things like logical AND, logical OR, addition, subtraction, and so on. These are all the binary operations. What I'm going to do is just imagine that I was the author of this code, and let's suppose I were really hasty when I wrote this, and I accidentally introduced a bug. So in particular, this case here for addition, currently it takes the arguments E1 and E2, and then it adds them together using C's plus operation. Now, what if I were hasty? What if instead of E1 plus E2, I had written E1 plus E1? That's a thing I could have conceivably written, and what's even scarier is that if I were to compile this, it would still type check and compile. Nothing would have caught me from making that mistake at that moment. So it's possible that this bug could have went unnoticed, but luckily our verifier is smart enough to catch these kinds of mistakes. So let's go ahead and see what happens if we try to verify the program now. So I'm going to rerun the verifier. Ooh, okay, so this is interesting. So this time it was not able to verify one of the proof goals. And it shows a counterexample for the one goal it was not able to prove. So I'm going to warn you, the output of the tool is pretty low level at this point in time. Basically what it's doing is printing out an internal representation of SMT solver proof goals. But if you squint really hard, what this is saying is that we're checking to see if a stream value is equal to an array value, and then on one side of the equation we have E1 plus E2, but on the other side of the equation we have E1 plus E1. And SMT solvers are really good about checking for these kinds of, broad equational theory kinds of things. And it is able to say, actually, no, those are not always the same. And it's able to spit out a somewhat difficult to look at counterexample, but a counterexample nonetheless of all the goals that we gave it. So luckily, the verifier was able to catch our mistake, and as the Copilot author, we could use this, hopefully with improved output in the future, to realize that, hey, actually, we need to have written E1 plus E2 instead of the incorrect code we wrote before. All right, well, that was a whirlwind tour of Copilot-Verifier, and I've demonstrated how you can use the verifier to take a Copilot spec and then prove that the generated monitor code is equivalent to the original spec. And there's some other interesting details about how the verifier works. There's some subtleties around the way we handle floating point operations, how we handle C operations that are partial, like dividing by zero and other things like this. But I'd have to get really deep into the weeds of implementation to properly discuss those things at the detail that they deserve. So I'm going to defer that. So if you want to learn more about how we verify programs with those sorts of things involved, I'd encourage you to check out the paper that we wrote about Copilot-Verifier. So I'll leave a link to that paper below. While the verifier is pretty capable at this point, we have some plans to make it even more useful in the future. For starters, we want to address this. This output right now is not super readable, and it can take some head scratching to figure out what it's actually telling you. So we want to make the error messages easier to read so that people who use the tool can more readily identify what the problems are. But even in situations where the verifier is able to prove everything, the output is still not as helpful as it could be. Now, currently, it'll just say something like, prove X out of X goals. But ideally, we'd be able to trace each goal back to the original Copilot spec and explain what it means. Some of the goals arise because you're checking stream values against array values. Some of them arise because you're checking if trigger functions fire in exactly the same ways. We ideally would explain where it comes from and then give you a sense of why these sorts of proof goals are important. The eventual goal here is that you could put this in front of someone who is trying to certify that your Copilot specification is trustworthy enough to be used in safety critical domains. And then they could look at the output of the tool, and that would make a convincing argument to this person doing the certification. All right, and then finally, the last thing I want to sort of hint at here is that all the work that I've shown up to this point has been talking about the C backend. But this is not the only way that you could sort of invoke Copilot at a low level. There's currently an in-progress Copilot backend for BlueSpec that's going to target FPGAs. BlueSpec is a hardware description language. What we want to be able to do is extend the verifier so that it can demonstrate that generated BlueSpec code is equivalent to the original Copilot specification, similar to how we do for C currently. The exact design of what this will look like is still a work in progress. We still have to figure out what exactly it means for BlueSpec code to be correct. So you'll have to stay tuned for future developments on that one. Anyways, that's everything that I wanted to cover in this demo. I hope you've learned some things about Copilot and Copilot verification from this video. So thank you for watching.